Hello, Chemistry 11 Honors. This is Mr. Chan. And today what I would like to do is talk about some simple gas laws that gases follow. Now, all gases have similar physical behaviors regardless of the physical makeup. Therefore, their behavior can be summarized by various gas laws. Now, one of them is Boyle's gas law. So Boyle's law says this. When you have a fixed volume, sorry, there we go. Oopsie, come on. For Boyle's law, for a fixed amount of gas at a constant temperature, the volume of the gas is inversely proportional to the pressure. So what you have is that there's an inverse relationship between pressure and volume. Okay, so if we wanted to keep a constant temperature, so let me show you what I mean by this relationship. So at a constant temperature, so take a look at the atmosphere here and take a look at the volume. Now, when I decrease the volume, let's say to about half, notice what happens to the pressure. The pressure goes up. Conversely, if I were to increase the volume, what happens is the pressure goes down proportionally. So there's a inverse relationship between volume and pressure. Now, if we were to make it into an equation, what would happen is if we took the pressure times the volume, we would get a value of K, where K is a constant for a specific gas. So let's say if we had one situation. So let's say we had situation number one, where we have P1, V1 is equal to K. In another situation with the same gas, we have P2, V2 is equal to K. If K is the same, what we then have is we can say P1, V1 is equal to P2, V2 if K is the same. Okay? That would be Boyle's law. Now, another law is Charles' law. It says at a constant pressure, volume is directly proportional to for Charles' law, volume is directly proportional to temperature in Kelvin. Now, the key thing is this. The key word here is Kelvin. This is key. In gases, when we do gas laws, we always take a look at the temperature is always in Kelvin. And recall, for temperature in Kelvin, you take the degrees Celsius plus 273.15. So what you have is volume is directly proportional to temperature at a constant pressure. Now, if we were to look at this again in our simulation, we have pressure, okay? So pressure and temperature. Let's see, oops, here we go. So what happens is if we change the volume, okay, notice we have to cool the temperature to maintain the pressure. Conversely, if we increase the volume, notice we have to heat the particles to a higher temperature to maintain the pressure. So that is what we have for, let me get this here, for Charles's law. The volume and temperature are proportional. Again, so what we can do is take this proportionality and say volume divided by temperature is equal to B, where B is a constant for a specific gas. So again, if we had different situations, situation number one, we would have V1 over T1 is equal B constant for a gas. If we use the same gas, so we have situation number two, where we have V1 over T1 or sorry, V2 over T2 is also equal to B, what we can do is we can combine it, and what you have is V1 over T1 is equal to V2 over T2. Okay. The third one is Avogadro's law. At a fixed temperature and pressure, the volume of a gas is directly proportional. So we have it here. At a fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas in the system. Now, when we talk about the amount of gas, it's either in moles or molecules. Okay, so V is directly proportional to N at a constant temperature and pressure. So again, if we look at the simulation, let me see here, let me just flip it to the simulation. So what you have is you have your, let me see here, constant temperature. Okay, notice I have a certain number of particles. So if I were to increase the number of particles, okay, what happens is at a constant volume, I increase the pressure, or sorry, at a constant temperature, I increase the pressure. And if I keep it at, let me see here, see if I can do that. Let's see, constant volume. Oh, it doesn't work on this simulation. Sorry. Okay. Let me go back here. So what you have is the volume is directly proportional to the number of moles. And again, if we were to take it into a relationship where we had situation number one, so I would have V1 is equal to A times N1. And situation number two, I would have V2 is equal to A times N2. Again, if A is the same, again, this is a constant for a specific gas, then what we would have is we would have, let's see, we would have V1 over N1 is equal to V2 over N2. Okay. Now, these three laws just tell us how gases will react, where pressure and volume are related, volume and temperature are related, and volume and the number of moles is related. Okay. Now, in this case, this Avogadro's law is where we came up with the idea of 1 mole of gas is equal to 22.4 liters. And later on, I can explain how we got that number. Now, if all three laws were considered simultaneously, it seems that reasonable that the volume of a gas should be directly proportional to the amount of gas and temperature and inversely proportional to the pressure. So if we were to combine all three of the Avogadro's law, Charles's law, and Boyle's law, and put it all into one, what we come up with is volume is directly proportional to the moles, to the temperature, and inversely proportional to pressure. And again, what you have is you have R is a constant. Now, so what happens is rearranging it, what you have is you get this PV is equal to nRT. This is the ideal gas law. Now, notice I've also given you this molar mass is equal to density times RT divided by P. What I can do is later on is I can explain how these two formulas are related. Now, for R, this is called the ideal gas constant. And depending on what units we're using for pressure, it has a different value. You can either be 0.082057, if you're using atmospheres for pressure, or 8.314 if we're using kilopascals for pressure. So what we have now is we have the ideal gas law. Again, what you have is if we had situation number 1, we would have PV is equal to nRT. And if we had situation number 2, what we would have is PV, let me just make 1, 1, N1, T1, P2, V2 is equal to N2, RT2. Now, again, if the R's are constant, okay, so what you can have is, we can manipulate this. So R will be PV, P1, V1, all over N1, T1. And this one would be R, let me just do that like that, is equal to P2, V2, all over N2, T2. Now, if R is constant, then what we get is we have P1, V1, all over N1, T1 is equal to P2, V2, all over N2, T2. Now, if N is constant, so the number of moles don't change, then what you get is you get P1, V1, all over T1 is equal to P2, V2, all over T2. This is called, if we look at this one, this is called the general gas law. Okay. So what it is basically a combination of all three of the Boyles, Charles, and Avogadro's all combined into one. Okay. Now, this ideal gas law that we have up here, PV is equal to nRT, okay, only occurs for ideal gases. Now, what is an ideal gas? Is basically the particles have zero volume and there's no attractive forces between the particles, and the kinetic energy of the particles is proportional to the absolute temperature. Now, what does that mean? It means that PV equals nRT only applies if there is, the particles don't have any volume and that there is no attractive forces. There's nothing, there's no attractive or intermolecular bonds between the particles. Now, to achieve this condition, you need low pressures and high temperatures, but the ideal gas law tends to break down at low temperatures and high pressure due to the fact that you have increased presence of molecular forces that form between the particles. Okay, so this ideal gas laws only works when the particles are super far apart. And how they can be super far apart is if it's low pressure and high temperature. But once you decrease the temperature or you increase the pressure, what happens is you're squeezing the particles closer together. And what happens is you have intermolecular forces that form, and therefore it sort of debunks the ideal gas law. Now, to compensate for this, I want just to quickly introduce the van der Waals forces. And to calculate the real life situation for gases, one needs to use the van der Waals equation, where you have P times V, but what happens is the P, this is adjusted pressure. And this equation here would be my adjusted volume. Okay. Now, the N and the V that you see basically stands for moles and volume, but what is this new A and B? So A and B are correction factors to pressure and volume due to the fact that at lower temperatures, intermolecular forces between the molecules exist. And this affects a molecule's ability to move freely to occupy available space. Now, you don't need to worry about this equation, but all you need to be aware of is the ideal gas law only occurs at high temperatures and low pressures because there's minimal to no intermolecular forces. But once the pressure gets too high or the temperature gets too low, what happens is intermolecular bonds start to form. And what happens is the ideal gas law starts to fall apart. All right, folks, when you get to class, there will be some homework to be given to you where you are asked to manipulate the general gas law or the Avogadro's law or Charles's law or Boyle's law. So please come to class and take a look at the board when you get a chance. Thank you very much. Have a good day. Bye-bye.